Okay, welcome back. It is now my pleasure to welcome our next speaker and my mentor, James Freericks, professor of physics and McDevitt Chair at Georgetown University in Washington, D.C. Professor Freericks obtained his Bachelor's of Science in Princeton, and he got his PhD from UC Berkeley. Professor Freericks has worked in a wide variety of different areas in physics. He has also won various awards, including the Kusaka Memorial Prize in Physics from Princeton and the Alpha Sigma Nu National Book Award. He's a fellow of the American Physical Society. And without further ado, I present you, Professor Freericks, to talk about robust quantum computing on NISQ hardware. It's all yours, James.
All right, thank you so much, Zhu Yao, and also thank you to the organizers for giving me the opportunity to speak here. I'll start out by just pointing out that this talk is really going to be focused on concrete applications on quantum computers that are available today. And I hope that I will convince you by the end of this talk that you can actually do some interesting science on the quantum computers that are available today. I want to start by acknowledging the people who I worked with on this work. I just want to pull up the laser pointer. Lorenzo Del Rey is a postdoc at Georgetown. Nate Ernest Noble is a staff at IBM. Akil Francis is a graduate student at North Carolina State. Barbara Jones is a staff at IBM. Lex Kemper is an associate professor at NC State. Brian Rost is a graduate student at Georgetown. Xiao Xiao is a postdoc at NC State. Efrata Zalecki is an undergraduate from Goucher College who worked with me on an REU project that I will be telling you about. And Ziyu Zhang was an undergraduate at Georgetown who did an undergraduate thesis. And then I just want to acknowledge the funders, which are Department of Energy for nearly all of the work. National Science Foundation provided a little bit of funding to Brian Rost. If there's time at the end and people are interested, these people here are the McDevitts, and they're the people who donated the money for the endowed chair that I hold. There's some interesting stories about them that I can tell you if anyone is interested at the end. To many of us, this is kind of what the state of quantum computing looks like. We're on the ground floor hoping we can make it up the stairs. This is a photo called Step Up by Mikito Tatasai. We're in this noisy intermediate scale quantum hardware. This is a term that was coined by John Preskill, and it corresponds to quantum hardware that does not have any explicit error correction put in as you would have in a fault-tolerant quantum computer. And the question he posed in the article where he sort of named these devices is, can we do real science on such machines? Other people like to call these near-term quantum computers. This is the term that IBM likes to use as opposed to NISQ. So you might hear both of those terms. I'm going to start by telling you a little bit about time evolution, because this is one of the most important aspects or problems in quantum mechanics that one has to deal with. In fact, I could say that essentially all of the research work that I do is in understanding time evolution. And the way that time evolution works is we have some operator that satisfies an equation of motion that its derivative is given by the Hamiltonian at that specific time multiplied by the operator. And you can formally solve this differential equation using what is called a time-ordered product, which is written here for you. This is a time-ordered exponential, and I'll get into a little bit more detail about exactly what that is. The time-ordered product is relatively simple for a time-independent Hamiltonian, but even for a time-independent Hamiltonian, putting it onto a quantum computer is somewhat difficult. And this is because the unitary operations that have to be applied in the exponent of the Hamiltonian, they all have to commute with each other. Otherwise, we don't know how to create the exponential of the operator that we're going to be applying. And there are many different ways to try to deal with that. And the first thing I'm going to talk to you about is something called Trotterization. And this comes from Herb Trotter, who is pictured here on the right. He was a physicist who worked at General Electric, and in the early 1950s, he said, you know, what the time-ordered product really is this ordered product where, at the latest times, I have the Hamiltonian at the latest time multiplied by some time interval, and then they're just some constants. And then I multiply it by the same thing evaluated at the earlier time interval all the way down until the first time interval. And you can see if you take the derivative of this with respect to the time at this time, because this is an exponential, it will pull down this operator and it'll sit in front of it. So this automatically is going to satisfy that differential equation that the time-ordered product has to satisfy. And if I have a time-independent Hamiltonian, this expression is actually exact because the Hamiltonian commutes with itself at all times. If I have a general time-dependent Hamiltonian, this is an approximate expression with errors that go like delta t squared. And then when we're thinking about making a quantum circuit, we have to break up each one of these factors into smaller pieces that can be expressed in terms of quantum circuits. So if I was looking at something like a Hubbard model, which involves hopping, electrons can move from site to site, and they interact when they're on the same site, I can break up my hopping into, if I'm on a one-dimensional chain, into hoppings that go from a site I to a site I plus 1 where I is an even site. And then I can look at the hoppings from I to I plus 1 where I is an odd site. Those two individual pieces, every term in here will commute with the other terms, and then these guys commute with themselves, but these two do not commute with each other. And then I can separately apply the interaction. So you could sort of break up your Hamiltonian into these three pieces. Because the fermions are not immediately expressible in terms of the qubits, we have to use something called a Jordan-Wigner transformation to do it. The actual implementation is a little bit harder, but this sort of gives you the idea of how that works. You would do this breakup for each one of these individual pieces, and then you would write a quantum circuit for each of the different terms. Now, in general, NISQ devices can only realize probably on the order of 50 C-naughts. Of course, you know, that it's really order of, and there's some calculations where people have gotten, you know, perhaps even an order of magnitude more C-naughts in a particular calculation. And I'll have more to say about that later. But this isn't going to get you very many Trotter steps because each one of these terms typically involves some number of C-naughts. And of course, I have to then repeat it for all the different Trotter factors. And this is one of the real problems with doing time evolution on quantum computers right now. We're limited to small systems. Lots of people are doing examples with 2-site systems, which aren't particularly big. 4-site systems and, you know, perhaps even as big as 8, 10-site systems have been done by some people. The most recent record that I'm familiar with is 55 time steps on an 8-site lattice, and that used about 500 C-naughts. And I'll have more to talk about that a little bit later. So one of the questions we asked is, are there alternatives to this? Are there ways to actually make this more efficient? And it turns out in some cases, you can actually construct an operator that performs the time evolution with the same number of steps or the same depth circuit for all times. And this works in a 2-site and 4-site Heisenberg spin model due to some special symmetries that the Hamiltonian has. And even with that, even with a constant depth circuit, the time evolution is still noisy. We looked at both 2-site and 4-site Heisenberg models. And on the 2-site model, it's not really all that bad. You should be comparing the colored dots with the corresponding solid lines. So the blue dots go with the blue curve and the orange dots go with the orange curve. And you can see that it's not that bad. The amplitude isn't quite right. But the period looks to be quite good in the quantum simulation. So it actually isn't all that bad. When we go to 4-sites, however, it looks a lot worse. I have a friend who likes to say this kind of looks like all you did was flip a coin and got a random result. Now, I think that's perhaps being a little bit too critical. And I'm going to show you that even though this doesn't look all that great, there still is actually quite a bit of good data in there. if you know how to extract it from the results that you got from the quantum computer. So I want to show you what I mean by that. Most of the errors that you get in the quantum computation can be corrected. The first are what are called state preparation and measurement errors. This says if you initialize the quantum computer in the state 0, some of the qubits are actually not in the state 0, and so that's going to be an error in your system. And as well, when you measure what the state is, if it's in the state 1, sometimes you'll measure that it's in the state 0. And by calibrating the machine, you can find out how often those errors occur, and you can actually correct for those errors and get a better measurement or a better estimation of what the correct result would be without these state preparation and measurement errors. And then there's another correction that is done all the time, and there's a little bit of theory that sort of explains why this should be occurring. But in general, this is kind of a fudge factor that we put into our calculations or our measurements to get results that agree better with calculations. What we do is we take our data, and the data here are the blue curves, and we're going to be just multiplying them. If they're a complex number that comes out, and we have to measure separately the real and imaginary parts, we will then multiply them by a complex number to boost up the signal and get it to look closer to the correct result. And this is a very common thing that's done. You might think that it is cheating, but there actually is there's some good reasons why this is a reasonable thing to do. If you have errors associated with what are called T1 decays, they will tend to give you an exponential decay. And in that case, you could even imagine doing something like multiplying by an exponential to correct for that decay. If you have something that is just gate implementation errors, those tend to just reduce amplitudes and modify phases, and that's essentially what this is trying to correct. And just to give you an idea of how that works, we calculated something called a dynamical spin susceptibility. And this is, not a trivial thing to calculate. It's going to tell us about the dynamics of this spin system as you flip spins and so forth. And the exact result is given for you here. Because it's a finite size system, it's a set of delta functions, and we're just plotting the weights of those delta functions. And I only get a couple of different delta functions because of the finite size of the system. When we look at the raw data, you can see just by doing a Fourier transform on the raw data, it's not that bad. There's some extra peaks and things, but it's actually already pretty close to the correct data. And that's because the period in that data, even though the amplitude was not right, the period was actually pretty good. If we then do the phase and scale correction, we get a result that is a little bit of an improvement from this one. You can see these incorrect peaks are getting reduced. But if we instead just try to fit the data to delta functions, we actually get fits with weights that are pretty darn close to the correct result. And what this shows you is that the results in Fourier space actually look much better. And when we error mitigate them and fit the results, we actually are getting pretty good data out of this quantum computer, even though the initial results didn't look that great. Now, we've extended these ideas to more general models using group theoretic methods of Cartan decomposition. And I'm going to just try to explain to you very briefly in one slide how this works. The idea is that I have a Hamiltonian. In this case, this is a transverse field Ising model. And the Hamiltonian has a set of interaction terms in it. And what we do is, in this particular case, we actually look at each of the operators separately. We calculate the algebra of that. We find the completion of that algebra. The Hamiltonian sits, and then we're going to separate it into two subspaces. One of them is called the M subspace. The other is the K subspace. The Hamiltonian sits in this M subspace, and it has a set of operators, an abelian subgroup of this M subspace that all commute with each other and include some of the operators from the Hamiltonian. And so this M subspace is the span of these terms. The K subspace is coming by looking at the commutation algebra of these operators with themselves. And then this operation called a Cartan decomposition, excuse me, allows me to write an exponential of terms in this M subspace as an exponential of terms in the K subspace times an exponential of terms in this abelian subspace times the Hermitian conjugate of the exponential of the same terms in the K subspace. And we actually rewrite this not as a sum of terms from the K subspace, but actually as a single set of factorized terms in that K subspace. And so what you can see we've done here is the change in the time evolution is governed by how this term changes as a function of time. But all of these other operators are exactly of the same form, and they get applied in exactly the same fashion for each time step. So this is a constant depth time evolution circuit. If I'm evaluating it for time t or evaluating it for time 2t, the only thing that is changing are the parameters that go into the circuit, but the actual circuit itself is always exactly the same. And that means that you could carry out time evolution to long times in quantum computers where you can do this decomposition. And this figure is showing you an example of how that works. This was not run on a quantum computer. This is instead done on a simulator. It's looking at a 10-site disordered transverse field Ising model. And we're comparing two different Trotter approximations, one that used 180 C-naughts, which is how many C-naughts we have in our constant depth circuit, and one that used almost an order of magnitude more C-naughts. And the error in the Trotter, initially the Trotter works very well, but then it starts to get large errors. And this is focusing on the error itself. And you can see the Trotter, which is in green, has orders of magnitude higher error than the Cartan decomposition, which has a nearly constant error, which is here about 1 part in 10 to the 7. And so this is in cases where you can do this Cartan decomposition, and we can get the quantum computers to give us enough ability to run on large enough systems where we can run the full circuits, then you really can do time evolution. You can start looking at complicated time evolving systems. Now, to do this Cartan decomposition for a time dependent Hamiltonian is actually quite a bit more complicated because you have to redo the Cartan decomposition at each time step. And so that makes things much, much more difficult. But for a system that has a Hamiltonian that does not depend on time, this is potentially going to be a very good way of doing time evolution in systems where the final circuit that you get is an efficient circuit that you can evaluate. Okay, the next thing I want to talk about is looking at topological quantum protection. There's been a long history of work that has looked at and has been discussing the benefits of working with topological qubits because they have this protection to errors. What I'm going to talk to you about here is something that's quite a bit different. We're going to be doing all of our calculations on a conventional quantum computer. We're working on the IBM machines, but we're going to be modeling topological models. And what I'm going to show you is that even on a conventional quantum computer, if you try to do a calculation of a topological quantum model, the topological quantum model has an inherent protection due to the topology and the conserved quantum numbers in the system that actually allow you to do much more robust quantum computation than you might be able to do in a system that doesn't have topological protection. So you actually can get topological protection just from the model that you're simulating. And here what I'm showing you is the Kitaev model. The Kitaev model is a model of interacting spins where the direction that the spin interacts changes according to the different bonds in the system. So some of these bonds involve ZZ interactions, some involve XX interactions, some involve YY interactions. And this model can be solved exactly, and it has a topological phase diagram where, as a function of these different interaction exchange coefficients in this intermediate region here, this phase, this B phase, has a different topology than the A phases have. And the way in which this is solved exactly is using Majorana fermions. You map the spins. I'll tell you a little bit more about exactly how that works in a couple of slides. So there are physical systems that look similar to this. This is a compound that has been one that has been of large interest in the condensed matter community called Herbert-Smithite, which has these kinds of connections that are similar to this Kitaev model and even has spin exchange that's similar to this. And Roman Orus has done a number of, quite a bit of work on this, and he looked at circuits that you can use to determine how to calculate these properties on quantum computers. The key is that this order parameter is a topological quantum phase transition. So there isn't a local order parameter that you can measure that says, oh, I'm in the ordered phase. Instead, it comes about by the fact that this system has gapless excitations in the topological phase, and the excitations are gapped outside of the topological phase. Now, the strategy for solving the problem involves many steps, but all of the steps are relatively simple. I like to call this French cooking because anyone who is out there who's a French chef who has done any kind of cooking knows that each of the steps in a French recipe is relatively simple, but there often are lots and lots of steps. And the way that this works is we convert the spins into fermions by using a Jordan-Wigner transformation. Then we decompose the fermions into Majorana fermions, and there is a Majorana braiding that converts into fermions and gauge fields. And then we do a Fourier transformation to position space, still in terms of the fermions and the gauge fields. And then we do a Bogoliubov transformation on the fermions into Bogoliubov bonds, and the Hamiltonian becomes diagonal in this basis in terms of the Bogoliubov bonds. And so by following these steps, you can actually create quantum circuits that will solve the Kitaev model on a quantum computer. And so this is showing you an example of how this works. This is looking at these Majorana circuits, and there are two kinds of braiding that goes on in the circuit. There's a braiding between the fermions that are defined at a single site, and then there's a braiding between the fermions at two different sites. And the circuit has a couple of different steps. This is the Majorana. We start off, of course, with the Jordan-Wigner transformation. This is the Majorana braiding part. Then we're doing the Fourier transform into momentum space, and then we're doing the Bogoliubov transformation. And these are circuit diagrams for the different parts of this circuit. So what we're interested in is trying to find this topological phase transition. And one of the common ways of doing that is by looking at something called the entanglement entropy. And the way that that works is I start from a larger system, I separate it in two by cutting it, and I look at the reduced density matrix by integrating out the second part, the second half that I've cut the system into. And then I calculate the entropy, the von Neumann entropy of this using the reduced density matrix of the A system after integrating out the B system, or tracing out the B degrees of freedom. And that's called the entanglement entropy. And if you look at that entanglement entropy as a function of these different exchange coefficients, there's a clear phase transition from one phase to the other. This is a blow up of one part of that triangle that sat in the center of that bigger triangle that I showed you the picture of before. Now, when we do the calculation on this four-site system, using a simulator, we get something that looks like this. Now, the transition is occurring here around 1, and frankly, aside from the fact that this is increasing, there's not a very good sign of a transition. Things get much worse when we run it on the quantum computer. On the quantum computer, everything gets reduced and flattened. This was this problem that I was talking about when I was showing you some of the earlier results, where we have to expand and scale results to get them to be more like what the true solutions are because of the errors and noise in the NISQ devices. And frankly, this is almost the same as a flat line, and it would be very hard to say at all that there's a phase transition occurring here. So there really are no signatures of this. And the question is, what are we missing here? So we went and we took the simulator and we looked at larger and larger systems, and we see, well, actually, it looks like you really have to get to a fairly large system on the order of 80 lattice before you can really start to see a kink, which is the signal of the transition in this system. And that is not something that we're going to be able to do on current hardware. We're not going to be able to run a quantum computation on 80 lattice sites with 80 qubits. I don't even know whether an 80 qubit quantum computer exists at the moment, although we're getting close that one could do such a calculation on. What this really indicates, however, to us is that there are important points in momentum space that are providing the signal that's giving the kink. And so if we could do our calculation with a sampling that tells us about those important momentum points, then we might be able to see the signal on a smaller system. And that's the strategy that we took. And we took an idea from condensed matter physics, which says, let's not work just with periodic boundary conditions, but let's change the boundary conditions. We have to do that change in a very special way that allows us to continue to do the Bogoliubov transformation. So we have to be able to shift both with a shift to the left by some delta K and a shift to the right by some delta K. And then when we do that, we can see a transition from a gapless spectrum, which is the black curve, which you can't really see very, very well here, versus the gapped a gapped versus a gapless spectrum. And this transition is being indicated between the black and the right. But I agree, you can't see it so easily here in this image. But when we instead look at that measure of the entanglement entropy, there's a large jump that we see. And this jump is very easy to see on the quantum computer. It is not as big a magnitude of a jump as we get with the simulator, which is the black curve. But this jump is incredibly distinctive. It's essentially flat on both sides with a very different number. And what we did was we now took this and we mapped out the phase diagram of this topological system. And this is the quantum the quantum computer data. The red is the region that is in the topological phase, and the blue is the region that is in the normal phase. And the orange line here is the exact phase boundary. And you can see that the quantum computer is essentially exactly giving us the phase boundary in this calculation. And this is arising because of the topological properties of the system. Now, we went on with this idea and looked a little bit further at Chern numbers. So a Chern number is one of these topological, you can think of it as a topological quantum number. It's essentially counting the holes in a torus, which is a conserved quantum number of the system. The way it comes up in wave functions is, here I'm plotting a plot of the phase of a wave function as a function of two parameters. And here it's two momenta. And if I look at this plotted, say, on a cylinder, using one of these axes as a cylinder, you can see this phase actually is winding all the way around 2 pi. So the phase actually winds around in a circle as I go across ky. If I look instead at a different instantiation of this problem, in a case where the topological phase is trivial, here the phase winds out a little bit and then winds back, and it never actually loops around the cylinder. So I don't loop it all around a circle in this case. So this would be a case that corresponds to a trivial topological phase, and this would be a case that corresponds to a topological phase that has a winding of 1. So this topology is determined by how the phase winds around in this base space, which in this case is momentum space. And to measure it, what we really need to know is, how does the phase change as I go from one point to another point? That means I have to be able to prepare the state at a particular point, prepare the state at a neighboring point, and figure out how much has the phase changed from one point to another. We then have to add up all of those changes to calculate the Chern number. It's essentially the same as integrating over the base space. And what we find is, because of the topological properties of this, that the winding is going to be an integer, we actually find that our calculations on the quantum computer are error-free. We really get integers, and the integers are exactly the integers that they're supposed to be. This can be used both for single particle states and for many body states that have topological properties, if you can create the many body state. And we use the unitary coupled cluster approximation in its factorized form to create these many body states, for an example that we did in this work that I'm showing you up here. All right, so what this shows is that topological protection of just the physical model, not of your qubits, not of your quantum computer, actually translates into a topological protection of the quantum computation on a NISQ machine. And we think that this is a pretty interesting result that comes out of that. A related idea to this is to look at zero temperature phase diagrams. And here what we're looking at is the XY model in a Z magnetic field. In this model, SZ commutes with a Hamiltonian. And the Z component of spin is then a good quantum number. And if we look at, these are the different energy levels, and the color corresponds to the different spin. If we look at this, we see that there are actually two level crossings in the ground state. I start on this blue line, I then go into an orange line, and eventually I end up in a pink line. And each one of these transitions is a change in the quantum number, the Z component of spin, as a function of the magnetic field here. I'm sorry, this plot is not labeled. This is energy on this side, and this is magnetic field on the horizontal axis. Now, there's a strategy that has been used to try to look at the ground states of complicated Hamiltonians called adiabatic state evolution. We had a whole talk on this by Dan Lidar 2 days ago, I think it was. We would like to use the magnetic field as a way of adiabatically changing the parameters in this model. But because this model has symmetry, those different states are not coupled. And I can't just use adiabatic state evolution to give me the different ground states. It won't work because the states aren't coupled together. And so the solution is to then, okay, well, we'll have to modify the Hamiltonian to couple them together. And this is indicated for you here. These are what the true phase transitions are, and this is adding a coupling, a magnetic field in the x direction, which couples all the states together, and then looking at how the magnetization changes as a function of field. We no longer get the sharp steps, but you can clearly see that they're transitions, and this transition we would take to be occurring at the point where the midpoint of this step intersects this line. So this would be the first transition, this would be the second, the third would be sitting almost exactly on the orange line, and so forth. And then what we would do is we would repeat the calculation for a different value of the x component of magnetic field, and then scale the results to that Bx going to 0. So that's indicated for you here, how we find those phase transitions. And then we would do the scaling. And we've actually run this on a quantum computer for the two-site system. So for the two-site system, there are only two phase transitions. We go from a spin of 1 to 0 to -1. We're going to be focusing on looking at each of these transitions separately. I'm going to really show you data only for this particular transition. And this is what the actual steps are. What we're going to be doing, we're going to be adding in an x component of the field, and we're going to be using a ramping of the B field that is according to what is called the local adiabatic evolution of the system. So the B field as a function of time is not going in a linear way. It's actually going in this kind of curved way. And this curved way is chosen so that it's going very slowly when the gap is small, but it's going more fast when the energy gap is large, so that at each time step, the amount of diabatic excitation that I get out of the ground state is the same for each time step. So then you have this more complicated ramping of the magnetic field. And I do apologize, these figures are a little bit more blurry. This is courtesy of Microsoft in converting from a PDF into a PowerPoint, but I don't have the original figures to show you in this PowerPoint. It's still, I think, pretty good. So the exact step is given by the black dashed curve. The blue curve is what we get by looking at the trotterized time evolution with a particular time step for this model that has a given value of Bx. And then the red curves show what the simulator gives for a circuit that essentially is working the way a simulator works as opposed to the way a hardware would work. And then from this, we would find the phase transition, which is where these lines intersect, and we would do a scaling analysis of that. Now, this is the data from the quantum computer, and you can see, just like with the other data, it's not coming all the way up to 1. It's coming up to a smaller value than 1. And so we're going to have to do our scaling of the data before we do the extraction of it. I'm not going to show you all the details of that. It's actually a fairly straightforward thing. And then depending upon how many points we use to fit where that transition occurs, you can then scale your results to Bx goes to 0. The exact transition is at this point, and these different scaled results are all coming pretty close to this. So this is really showing you as a proof of principle that this technique is working. We really find quite good results of this, and we're now looking at extending this to some larger systems and seeing just how far can we push this on the conventional quantum computers. So the last illustration I want to give you is on what happens with driven dissipative systems. And the first question you might ask is, why do I care about driven dissipative systems? Well, it turns out a driven dissipative system, and what I mean by this is I'm applying something like an electric field to a collection of electrons that are moving on a lattice. And then I'm attaching the lattice site to some kind of a reservoir that can exchange energy with the system. And because when I drive it with the electric field, I'm going to be creating heat via Joule heating. If I'm attached to a reservoir which can pull the heat out, I eventually can get to a steady state where I can have a DC current flow given by the electric field. This is what happens when I take a piece of metal and attach it to a battery. But it turns out that this problem, the quantum mechanical description of this problem, was really only worked out in the 1960s. And the first classical computations of this really started around the 1990s. And it still is one of the hardest problems to solve using classical computation. I would say we still do not have a general purpose way of solving these problems with classical computers. And so this is a realm where if we could even just solve exactly one of these problems on a quantum computer, we're already doing better than what a conventional computer can do. So this is a place that's really ripe for quantum advantage. It's also very important for science because this is an area that there's a lot of very interesting experiments done. One of them are so-called pump probe experiments in condensed matter physics. This is a case where you take a very high power laser with a femtosecond width pulse of light that you shine on a material, and then with some time delay in the few femtoseconds, you study what happened to the system as a function of time after you applied the pump to it. There are these billion-dollar machines called X-ray free electron lasers that do these kinds of experiments. This is right at the frontier of ultra-fast and non-equilibrium condensed matter physics. We also have experiments that are done in ultra-cold atomic gases, where people can very precisely tune their Hamiltonian, very precisely tune exactly what they are, what kinds of fields are driving they're doing to their system, and they can then study the non-equilibrium dynamics of these systems. So there's a lot of experimental data available for these kinds of problems as well. The main restriction that we have on conventional computers is these problems get harder and harder the longer you're trying to run your simulation. So most calculations on conventional computers are restricted to short times. And the question that I'm going to be talking about here is, could this be the killer application on quantum computers, even NISQ devices? Okay, so let me just give you a setup of it on how this works. You can look at this as lattice sites on a one-dimensional chain, and the electrons can hop from one lattice site to the next lattice site, or they can hop back. They can hop in either direction. And then each lattice site is coupled to a reservoir, which is schematically indicated in blue here. There's some spectrum given by that reservoir. It's an electronic reservoir, so it actually, the electron, instead of just hopping along the lattice, it can also hop into the reservoir, and it can come back out of the reservoir. But it can't hop between the reservoirs. Each of these reservoirs is independent of each other, and the reservoirs are kept in thermal equilibrium at some temperature. So this is how we exchange energy and particles with our reservoir. And it turns out that if the electrons don't interact with each other, if they're not interacting, this problem can actually be solved exactly. And the exact solution is given by this blue curve. And one of the approximate methods that is typically used to solving these things are called master equations. And I'm plotting for you two different master equation solutions. The red one is a master equation solution that's called a Redfield master equation. And the black one is a master equation that's called the Lindblad master equation. And both of these result, they're clearly approximate, but they have the same general qualitative shape, and they're even quantitatively accurate over a wide range. They clearly don't quite get the peaks right, but they're really pretty good. And the reason why I'm mentioning this is that when you work with a master equation, what you do is you integrate out the degrees of freedom of the reservoir, because the reservoir is a non-interacting system. We always choose the reservoir to be non-interacting. And it maps the whole problem onto simulating a complex system. So we have the electrons hopping on this lattice, plus complicated stuff which replicates the behavior of the reservoir. And that is the kind of a problem that I can immediately put onto a quantum computer. And the thing that's very interesting about it is that because of the way that this problem can be solved exactly, I'm actually able to solve the infinite size lattice system with an infinite number of reservoirs, and each reservoir is infinite in size on a NISQ device today. And I'm going to show you how that works. So the strategy is that we start with that Hamiltonian plus reservoir. We extract the master equation that approximately describes it. We then construct something called a Krauss map that will implement the master equation in a trotterized form. And from that Krauss map, we will then derive a quantum circuit that implements the Krauss map. And this is an example of a quantum circuit that implements a Krauss map for this problem. Now, in this calculation, there's this gate that is indicated by a 0. This is a reset to 0 gate. Krauss maps are not unitary. They are irreversible. You have to have an irreversible process to simulate a reservoir on a quantum computer. That irreversibility can be simulated by using a reset. Now, when we first started working on these problems, resets were not available on quantum computers. So one of the ways that you can implement a reset on a quantum computer that does not have mid-circuit measurements is that you couple with an ancilla. This is an ancilla. You couple with these two ancilla to the system, and then you, at the end of this step, when you want to implement the next step, you bring in a fresh new ancilla, and at the end you do a measurement. Because you're not touching the original ancilla and you measure it, it is like you did that measurement during the circuit at this time. And that's what we did with these simulations. So this is what the exact solution would be for this master equation. And then we have to do trotterization with a large time step because we can't do very many trotter steps. And this is what the trotterized circuit looks in blue. And then if you just blow up this front region, this region here of the single first period, this is what it looks like. And this is what we actually ran. So this blue is this ideal, which is in blue. And then these are our quantum data in orange, and it's actually working quite well, but we could only go 5 steps. We couldn't go any further because then we had to do so much swapping given the connectivity of the system to bring in new ancilla that we just ran out of gas. We couldn't run it anymore. But from this and from the fact that we know exactly what the steady state is, we can then just directly prepare the steady state. And so we did that too. And this is showing tomography of what that steady state is. The exact results are here that you should be comparing with the quantum computer results. And you can see that they actually work incredibly well. You can't, there are some small differences, but you can actually do this kind of state preparation very well on a quantum computer. So this seemed very promising, but it suffered from the noise and the errors and really from the fact that I couldn't go that far out in time. But then IBM introduced partial resets on their hardware. And this, I believe, is really a potential game changer. So what I'm going to show you now is some preliminary data that we have. We are writing these results up, and we do expect to be submitting this in the near future. I want to first just go over again what the conventional time evolution is. And I think the most impressive time evolution that we've seen so far is from the Google group. You can see it's a giant group, to do these kinds of calculations. This is like a high energy physics team. This is their results. And what they're showing you here is essentially their raw data. The exact result are the solid lines and the data are these dots. They then go through a number of different steps, but effectively what they're doing is this scaling. And this is a situation where you can clearly see their data is exponentially decaying. So they're effectively going to be boosting up that signal to get their final results. And so they have a couple of different steps. They have a post selection, they have something they call flow calibration, and then they have this rescaling, and their final results come out really quite accurately. But the error bars are huge. I mean, the error bars here at the end are about as big as the total extent of the data. So, if you're a believer, you would say, yeah, they nailed this. They got the time evolution all the way out. They certainly have it out at least to 25, 30 steps. It does require significant error mitigation. And this is really a very impressive calculation that's been done on NISQ devices. So this is what we get with a driven dissipative circuit using resets. We did 400 time steps, and you can see this, the fact that this isn't coming all the way down. This, again, the orange line is the exact result. The blue are the quantum computing data. The reason why it's not coming all the way down is due to T1 decay. This is the same issue that we always have in quantum computers. We have to do rescaling. But you can see that we're seeing no degradation of our signal out to 400 time steps. And the reason why the result is oscillating is this is what's called a flow case system. It's because when you apply a DC field on non-interacting lattice electrons, they undergo something called block oscillations, which creates actually an AC signal. Excuse me. And that oscillating signal continues forever. And so that's what we're actually looking at, is this oscillating signal. What we can do is we can actually do this calculation, changing the number of resets we do at each Trotter step to do something similar to Richardson extrapolation to extrapolate our results. So this is results for 4, 3, 2, 1 resets that are then extrapolated to no resets. And that's the red curve. And the black curve is the exact result. And I think you can see that when we put in relatively simple error mitigation, the results that are coming out of this quantum computer are nearly perfect. So we're now looking into ways that these results can be extended to actually allow us to simulate these pump probe experiments from condensed matter and chemistry. And so I'll repeat the question that I started this talk out with, which is, have we found the NISQ machine killer application? We think we have, and stay tuned. We're still working on this problem, and we'll let you know exactly how it goes and what we end up with. But we think that this is really a very promising application on NISQ machines that will let us do science that you can't actually do on conventional quantum computers. And so I'm going to then end my talk, leaving some time for discussion at the end. I just want to acknowledge the people who worked on this project. This is Lorenzo Del Rey. This is Akil Francis, Lex Kemper, Brian Rost, Xiao Xiao, Frada Zalecki, and Ziyu Zhang. And of course, again, I'll just acknowledge that we got funding from the Department of Energy, and then a little bit of funding for Brian came from the National Science Foundation out of their KiziNet program. And I'll be happy to take questions and discussion at this time.
All right, thank you, James. So looks like we'll have you back again next year for the update. So, is there any question for James? Do you have any question for James? Can you actually talk about the churn number that you mentioned and how it relates to the conclusion, perhaps?
In this case, the churn number is really counting the winding of that wave function. Let me get back to that picture. Sorry, this is the way it works with PowerPoint. So if you look at so this is the phase of the wave function. And if you just, ky is a periodic variable. So when I come from here, I'm going to end up back here. So if you look at this, it's pointing up, it's turning to the left, it's pointed all the way down, and then you can see it then keeps winding and coming all the way back up. If you like, if you think of mapping each one of these directions to a point on a circle, we've really wound all the way around the circle. So when I look at the phase of this wave function as I vary over this periodic variable, it winds by a full 2 pi.
Mm-hmm.
The fact that it wound by a full 2 pi, if I take that 2 pi and divide it by 2 pi, that's the integer. That counts the number of windings. That's the Chern number. Okay. Now, if I look at this example here, you can see it starts winding out, but it doesn't get all the way around. It wound around maybe to about 10 o'clock, and then it starts coming back. So it essentially wound around and then came back. Mm-hmm. And so what it's doing here is it's doing something where it's not winding fully around the circle. So the net winding on this is 0. So there's no net effect. But then the way that we do the calculation is we are actually just calculating the little bit of winding that it's doing from one step to the next step. And then we just accumulate that over the full range as we move over the base space. And what we find is if we have a small error at one step, it gets compensated at the next step. And in the end, we actually end up getting an integer that comes out. So that when we run this on a noisy quantum computer, the answer that we get that comes out is an integer. And so it's actually calculating these Chern numbers exactly for these systems. And we've been able to do it both for, this is a single particle wave function, but we've been able to do it as well for a many particle wave function. We did a 2 boson wave function. We were able to also do this for.
So this Chern number has a topological implication that provides the robustness of the corresponding, was it the simulation or the?
Well, the algorithm that is used to calculate this Chern number seems to be robust to errors and always gives an integer. That is not true of every topological quantum number or every way that you would measure this topological quantum number. We looked at some different ways of measuring this, and in the different ways that were measured, they weren't quite as accurate. They didn't always give integers, but we typically will see things that look like this, where you can clearly see that there's a jump. And so even if it's not perfectly robust, there's enough robustness that these things that are sort of changing by discrete jumps end up being very easy to identify on these NISQ machines. And this is how you can take the topological protection of the model and translate it onto a machine that has no topological protection, and yet your calculations will work a lot better because of that.
Okay. Any other question for James?
Yes, I have a question. My question is whether will we be able to use full-blown quantum error correction to protect, NISQ era devices from noise? Is it possible, or we shouldn't aim for that?
So I am not an expert on error correction, but my understanding is that if you implement an algorithm in the appropriate way with the way that you must for a given error correction protocol, then as long as the rate at which you create errors is small enough, they typically can correct single errors over some time range, and you check to see whether there's a single error over that time range, and if there is, you correct it. If you get 2 errors over that time range, then typically you can't correct that. I'm sure there are error correcting codes that can correct multiple errors over a particular time range as well, but there's always some limit. So, but with a fault tolerant machine, if you really can correct these errors, then then you're going to be in good shape, and you can do, complicated fault-tolerant quantum computation. We might have to wait until after our lifetime for this to occur. I mean, they're talking about, thousands, if not hundreds of thousands of physical qubits for one logical qubit that can do this. And if I need to have hundreds of logical qubits to do a calculation, and I'm going to be running depths of millions of circuits, these quantum computations are not going to be very fast. They're going to be hard to carry out. And I think that for many, many years, we're going to be thinking with NISQ mentality in how can we come up with a robust, low-depth way of doing it, even if we have a fault-tolerant quantum computer, because it'll do the calculation better. So I think there's going to be, for a very long time, if not forever, need for thinking in terms of what are the robust things that we can calculate, what are the robust algorithms we can implement, and how can we do that to get out results that we can't get from conventional computation.
Very nice, thanks.
Tell us about the McDavids.
So that's a good story. We do have some time.
Yes.
So I'll get back to their picture. So back in 1900, this guy, McDevitt, his mother was the secretary of a guy, his name was, I think it was A. Ward Ford. And he had a company that made punch time clocks for workers. Back at that time, some of them had little punch cards, but others, the workers had a little key that they came in and they would turn the key to say that they arrived at work. And she was the secretary of his company. She invested $100 in his company. She borrowed $100 to invest $100 in his company. And this guy, at that time, there were 3 other companies that were making time clocks. And there was a 4th company that was making punch cards, which were often used in the time clocks. And the 4 companies joined together and became the American Time and Calibration Company. And he was the chairman of the board. And he hired a guy named Thomas Watson to run the company. And they decided to change their name to International Business Machines. And during this guy's life, that $100 investment, they just kept reinvesting it in IBM stock. They never took a cent out. At the time he died, he was the single largest stockholder of IBM stock, and he was worth $750 million. And he gave something like a quarter of that to Georgetown. So that $100 investment became $750 million. So yeah, if you guys find the right startup, go ahead and invest your $100 in it.
But why Georgetown?
So he's a Georgetown alumnus, and he was a very religious, he was Catholic, very religious guy. He also gave some money to a Catholic school that his uncle was a physics professor at in upstate New York, which is where he lived. And I think most of the rest of his money he probably gave to different forms of Catholic charities.
I see. Okay. One last question for James. Anyone? Okay. If not, we thanks James once again, and hope to hear some updates from you. Thank you, James.
All right. Thank you so much.